In this video, I'm going to point out some functions whose graphs I want you to know by heart. For some of the techniques we're going to talk about in the future with respect to graphing, it would be nice if you already knew what these basic graphs look like. I refer to this as the library of functions, but it's probably better described as a library of graphs of these functions. We're not doing anything super complicated. These are all pretty We're not doing anything wonky here. These are all pretty standard functions. Don't say that. The first one is the graph of f of x equals x squared. And the graph of f of x equals x squared is a parabola that emanates from the origin. Its vertex is at the point 0, 0, and you get this curved shape that we call a parabola. Its domain is all real numbers. Its range is restricted because it has a lowest point. And you know that numerically because when you square a real number, you can't get a negative result. The smallest possible output you can get when you square a real number is 0. So the range is restricted from 0 to infinity. It starts by decreasing until you get to x equals 0, and then it increases after that. This is the graph of the squaring function f of x equals x squared. The square root function f of x equals the square root of x is like a half a parabola turned on its side. Instead of opening vertically, it opens horizontally, it opens to the right. But you only get the upper half because this notation refers to the principal square root, and so we're not going to get any negative outputs. As such, the range is restricted to 0 to infinity. The domain is also restricted because we can't plug any negative numbers in for x if we expect to get real number outputs. So the domain is from 0 to infinity. This function only increases. It increases over its entire domain. I know I've drawn it so that it looks like it's leveling off, but it's actually slowly increasing because the bigger the input to this function, the bigger its square root. I know it looks like this graph is leveling off, but it's actually increasing slowly because the bigger the radicand is, the bigger the square root will be. So again, I think of this square root function as a half a parabola that's turned on its side, that opens to the right. The absolute value function, absolute value of x, is a V shape rather than a U shape. It gets these nice straight edges. It's basically like we took the line y equals x and we snapped off the side in quadrant 3 and instead put it up in quadrant 2. This is a 90-degree angle here. The domain is all real numbers. You can plug any number you want in here. The range is again restricted because when you take the absolute value of a real number, you always get a non-negative output. The smallest possible absolute value you can get is 0. Just like the parabola, it decreases until you get to x equals 0, and then it increases after that. This is the graph of the absolute value function. The cubing function, f of x equals x cubed, this might be one that you're not as familiar with. It starts down in quadrant 3 and it's concave down until you hit this point here, and then it kind of turns and switches to concave up. It's increasing the entire time. Because the cube of a negative number is negative, we wind up with these points down in quadrant 3 rather than having points up here like we do with the squaring function. So we wind up with this curve that swerves through the origin. Its domain is all real numbers. You can cube any number you want. Its range is all real numbers because you can get negative outputs from cubing something. It's increasing over its entire domain. This is the graph of the cubing function. The cube root function also increases the entire time, but it's not nearly as steep. It snakes through the origin more horizontally than you see with the cubing function. Its domain is all real numbers. You can take the cube root of any number you want. It's okay to take the cube root of a negative number. You'll just get a negative output. As such, the range is also all real numbers. And again, even though it looks like I've drawn it so that it levels off, it's actually slowly increasing this entire time. The bigger the number you plug into the cube root function, the bigger the cube root will be. This is the graph of the cube root function. The last one we've actually seen before, but I just wanted to generalize it. If you have the square root of the difference in some number squared and x squared, the graph of that is the upper half of the circle of radius. If you have a function of the form square root of a squared minus x squared, its graph will be the upper half of the circle of radius a centered about the origin. So the domain will go from minus a to a. The last graph is one that we're already familiar with, but we're just going to talk about it in general. If you have a function of the form square root of a squared minus x squared where a is a positive number, if you have a function of the form square root of a squared minus x squared, we know that that's a semicircle centered about the origin. It's the upper half of some circle. If we make sure to be careful to say that a is positive, then we can say that it has radius a. The domain ranges from minus a to a. The range is restricted from 0 to a because we only have the upper half of the circle. The function starts off by increasing on the interval from negative a to 0, as you see here, and then it decreases after that. It's decreasing on 0 to a. I think it's a good idea to have these basic shapes memorized. We're going to run into these from time to time when we're talking about graphing techniques. And of course, you could always just throw one of these into your calculator to see what the graph looks like. But for the purposes of following the discussion, it would be nice if you knew what the graphs were off the top, so that when you see me draw a half parabola turned on its side, you know exactly why I'm doing that. It's because we're talking about some function related to the square root function. So take a little bit of time to familiarize yourself with these graphs. I think it will make a couple of the future lectures easier to follow. Let me know if you have any questions.